Greetings everyone. Today we are here to solve another integral which is 0 to infinite cosine of x over x square plus 1 dx. Well, we can actually solve this using the complex analysis, but today we are here to solve this with the Laplace transform. Well, before we do this, we should name this as I of alpha is equals to 0 to infinite cosine alpha x square plus 1 dx. Well, when plugging alpha equals to 1, we'll get alpha of 1 is actually the required integral. So now let's take Laplace transform. Laplace transform of I of alpha is equals to 0 to infinite, another 0 to infinite, cosine alpha x over x square plus 1 dot e to the minus s alpha d alpha dx. Well, we know that the Laplace transform of cos alpha x is equals to 0 to infinite cos alpha x dot e to the negative s alpha d alpha. Well, we are integrating with respect to alpha, so you can see that we can write by taking this part as Laplace transform of cosine alpha x. And we also know that the Laplace transform of cosine alpha x is s over s square plus x square. Terribly sorry about that. S over s square plus x square. Well, now plugging this value there, we'll left with which is equals to 0 to infinite Laplace transform of cosine alpha x over x square plus 1 dx. Well, we now know that the Laplace transform of cosine alpha x is actually this one. So by plugging this value there, we'll get 1 over x square plus 1 dot s over s square plus x square dx. Well, now doing some partial fractions here, we are left with s over s square minus 1 parenthesis 0 to infinite 1 over x square plus 1 minus 1 over x square plus s square dx. So s over s square minus 1. Well, this is actually, we know that the tan inverse of x minus 1 over s tan inverse of x over s from 0 to infinite. Let's move on to page number 2. And by plugging this value there, we know that tan inverse of infinite will get pi by 2, and the other value will become 0, same as here. So we're left with pi over 2s. Well, wait, let me erase this. So we can do some simplifications here. We're left with s minus 1, s plus 1 dot. Let's take the pi outside that, and we can solve this as s minus 1 over 2s. Well, you can clearly see that the terms which are going to cancel each other out, which is s and this s minus 1 and this s minus 1. So pi over 2 into s plus 1. Well, this is actually the Laplace transform of I of alpha, which is pi over 2s plus 1. By taking Laplace inverse both sides, and we'll have I of alpha is equals to Laplace inverse function of pi over 2s plus 1. Well, we can take the constants out there, so we'll left with pi over 2 Laplace inverse of 1 over s plus 1. Well, we know that the inverse Laplace of 1 over s plus a is actually e to the negative a t. Well, in this case, we'll have e to the negative a alpha. Well, those are just dummy variables. We can put anything. So we can write the above inverse function as pi by 2 times e to the negative alpha a. Well, by plugging a equals to 1, let's move on to page number 3. We'll have pi over 2 times e to the negative alpha, which is of course I of alpha. By plugging alpha equals to 1, we'll have I of 1, which is the recurrent integral, we'll have pi by 2 times e to the negative 1. So we'll have I equals to pi over 2 times e. It's a gorgeous looking answer we have here. And that's it for tonight, guys, and we'll try to solve another type of integration using the complex analysis. Until then, bye bye from Abhi, and please do subscribe my channel. Thank you.